Okay, so this will be a bit shorter. This is the second part where we talk about the software itself. Could you maybe close the door, please? So just a quick recap after the break, after the fika. Then we'll have, so we'll talk about the ansatz and the equation of motion in the recap, and then the observables that we can construct with the different, with the composition that we have. Then we'll look at this software structure itself, input files and executables, the source, and then the integrators. We actually already looked at it a bit, so maybe we can skip that. And then I'll present the workflow of the program. So how you do, you obtain ground state physics information, dynamics, and how you do the analysis to obtain the observables that you want. So let's start with a bit of recap. So we have ansatz and equations of motion. The ansatz, I rewrite it here. This is the decomposition where you have the time-dependent coefficients and the configurations. And the configurations are obtained by symmetrizing the Hartree product of different orbitals. So I will constantly refer to coefficients and to orbitals here. Those are the equations that the quantities that we optimize with the equations. And decoupled equations of motion are here again rewritten. So H is a given. I mean, the representation of H is not given because you have to construct it, but the one body part and the two body part of the Hamiltonian, you're supposed to have them from the start. The coefficients are contained in this vector, like we said, this big vector C. And then the orbitals are this phi j dot, and phi q here. They appear in the orbital equation of motion.
Subscript there is for R, or is it for the orbital j? No, it's for the.
No, you can think of, no, those are actually, this indexes the orbital itself. But you can think of an orbital as a vector.
Yeah.
So
okay, it's for the orbital.
Yeah. So this is like a vector quantity that where the vector is the discretization of the space. And then those rho quantities, those are the one body and two body reduced density matrices, and those are calculated from the many body state as we saw. So now let's come to the fun part. What kind of observables we can construct from our many body decomposition? So since we have the full many body state, we can in principle extract any observable from it. The most straightforward one is the energy. That's also what we use to kind of check convergence for ground state relaxations. This is just the overlap of the Hamiltonian acting on the state and then sandwiched with the state itself. And it can provide information about, for relaxations, whether you have bound states or scattering states. If you do the analysis after, you can also get information about the single components of the energy. So how much is the kinetic energy, how much is the potential, how much is the interaction. If you want to see, what is the contribution, is it strongly interacting or is it mostly just kinetic and so on. And for relaxation, like I said, it provides information about convergence. So it can tell you how quickly and how precisely it goes to the ground state as you do imaginary time. This is taken from the tutorial. And then for propagation, it tells you information about how the system is changing with respect to deviations in energy in time. So if you do quenches, for instance, like we do in the tutorial, you start from a state that has a certain energy, but then the Hamiltonian, the time-dependent Hamiltonian or the quenched Hamiltonian has a different set of parameters. So it would like for the state to go to a different energy, and you can track how fast this goes with the change in parameters. And you can see, like, if you do in this case a very fast quench, it will kind of go to a completely different energy. If you do slower quenches, depending on the parameters, the path towards the energy is different, but in the end you go to the same energy. There's some sort of adiabatic turning on of the interactions, if you want.
Sorry, what is imaginary time?
Imaginary time is literally time that is imaginary. So you, instead of doing propagation in real time, you use an imaginary number, and that is the same as having a temperature. And you go from a high excited state, so like a high temperature state, to progressively reducing it to go to the ground state. So in the equations of motion, it's literally done by using time as an imaginary number. You had a question, yeah?
Yeah, how do you specify initial conditions?
For the relaxation or for a time dependent
Just
product?
like in this program, this is the thing you put in, right?
So there is different ways of doing that. I think I'll mention something later. So you can either just choose a random initial state. That's the standard, and it's already coded. So when you start a program, it starts from some random noise. Or you can give, if you know, I want to start from this specific state because of certain interesting properties and it will converge faster or whatever, then you can you can code it yourself and give it as initial state. There are some pre-coded states, like in 2D, you can start from the eigenstate of a harmonic oscillator. So it's kind of like a blob. And then another way of doing things typically is relaxing the state into a certain Hamiltonian. So you basically start from the ground state of that Hamiltonian, and then you use that as initial state for a different relaxation or a different propagation. So very often then, if I want to look at a system that has to be symmetric, then if I start with noise, it's not really symmetric. It's better to start with something that is already symmetric. So I can start with doing a relaxation in a harmonic potential, and then the ground state would be asymmetric, and then I use that for the initial states for the next calculation.
And could you, with imaginary time, sometimes you pick your guess state to have the right symmetry, and then you get to the ground state, and if you take another symmetry, you get to the first excited state.
Yeah, sometimes I never done that, but that's a good idea. Yes, it's something that you could try. Yeah.
Sort of related, is there an easy way to impose a symmetry with an additional Lagrange multiplier, for example?
Yes, I think you could do that, but then you would need to modify the codes a bit. I mean, you really need to go into the guts of the code to modify things. Okay, so we talked about energy. The next best thing or easiest thing to calculate is the density. The density is as a real space, density distribution is just the density operator sandwiched between the state. And that gives you information about just how the state looks like in real space, or how its kind of average looks like. So it gives you information about localization, clustering, fragmentation, the works. And is the first kind of most obvious thing to do if you want to see how the particles behave and localize. So I give you here an example. This is for 5 bosons in an optical lattice with some long-range interactions. And you see that, 2 localize here, and then 2 localize in the middle, but they're kind of fragmented. They're sort of split. And then this is the equivalent in 2D, where you have different localization properties of, I think here might be different number of particles, I don't remember. It might be like 5, 6, and 4, something like that. But you can see how they localize in real space.
It is published, right?
It's accepted, yeah. Not yet published,
right.
But so another quantity that you can calculate is the density distribution by the momentum space. This is also very important if you want to get information about periodicity in real space, or if you want to calculate certain order parameters for instance, to track the transition between a superfluid to a Mott insulator. You can calculate the momentum space distribution, and then the height of the peak will, at K0, will tell you whether you're in a Mott insulating state or not. So it can help you identify phases. And this is an example of how it looks like in a work.
What question is this? The occupation number, or is it really the Fourier transform of the density?
Mhm.
And the density is psi r dagger psi r. If you transform that, you don't get.
That's the momentum distribution, this, I guess.
Yeah.
You will ask about something else, that if you can Fourier transform the real space density as well.
I mean that the Fourier transform of the real space density is the structure factor.
There is also that in the code, yeah.
And this is the momentum distribution.
Yeah. So this is the Fourier transform. Okay, I should have said Fourier transform of the operators that you then plug in. Yeah, but you can also do the structure factor, the static structure factor. So then we come to things that are a bit more interesting, which are correlations or quantities derived from reduced one-body density matrices. We already saw the one-body reduced density matrix before in the previous lecture. So this is nothing but the same formula for the density, but where you have R and R prime instead of just the same R. And this basically tells you information about coherence of the particles. From there, you can also get a normalized version of that, which is called the Glauber one-body correlation function, where you simply take this quantity and you normalize it by the density at R and the density at R prime. And that is a measure of coherence. So it gives you information about coherence and interference. So it's a measure of one-body correlation. And also we saw before that when you diagonalize this quantity, you get information about the orbital occupation. So you get the natural orbitals and the natural occupations. And that gives you information about how many orbitals are occupied, their population, and whether you're converging or not to the physics you want to map out. You can also do that for the two-body reduced density matrix. So that is the same principle. I think there's some error here. I think I didn't update the equations. These equations are wrong. This should be, that's weird. Okay. It was just a slide that was copied twice. So this is just a visualization of the G1, so of the Glauber one-body correlation function. And you can see a state where everything is diagonal, so everything is kind of like in a Mott insulating state. But here, this state has correlation across, these two blobs. So there is, it's not completely Mott insulating, it's still some superfluid characteristics. Now that we can do the same for the two-body reduced density matrix, so we can extend this construction of standard chain creation and annihilation operators between the many-body states. And if we do it for R and R prime for both, the complex conjugate and then the direct wave function in the integral, we get the diagonal part of the reduced two-body density matrix. And by doing the normalization like before, we get the two-body Glauber correlation function. And that really gives us information about real two-body correlation. So what is the effect of taking a particle at one point and placing it in another point? What is the correlation between those two? This is an example of how it would look like in some simulations. And like I said, it provides information about two-body correlation, like correlation holes for bosons bunching or anti-bunching. So if particles want to stay together or be apart, it could give you information about blockades from Pauli blockades due to exclusion principle or Coulomb due to long-range interactions. So it can give you more information about how the particles behave with one another. I didn't put it here in these slides, but both quantities can also be calculated in momentum space. So you can also have momentum space one-body correlation and momentum space two-body correlation.
And this correlation are dependent on time.
Yes, yeah. So it's equal time correlation, but it can change over time as you do your propagation.
Can you do correlations in time as well?
In principle, you can, but it's not implemented yet.
Okay.
Yeah, but it's a very good thing because then you can get information about the dynamical structure factor, and from there you can get information about excited states. So that's something that we are working on, and yeah, we're so excited about it. Yeah. Yeah, you can get OTOC and all these things as well. Yeah, it's a thing that we're looking into. So there's many more observables implemented in the code that I don't really have time to go through. I will just give you a list, a non-exhaustive list of things that are already implemented. So, you might think of, oh, I need that. So you know that it's there. We can calculate variances of all the observables we mentioned. We can calculate higher order correlations. So extending this Glauber correlation functions to 3-body, 4-body, n-body. We can calculate any type of overlaps of the many-body state with itself or with a modified version of itself. So we can get fidelities, autocorrelation functions, survival probabilities if you have some dynamical process and you want to see, a bear tunneling through a bear and you want to see whether it goes through or not. We can get single-shot simulations from the many-body wave function. That means basically taking a snapshot of the density and see how it collapses given the probabilistic nature of the many-body state. So you define basically binning of your space, and then you see how many particles have collapsed in the first bin, how many in the second, and the third. And then you can repeat that for many different shots, many different times. And then you get kind of like, by averaging over that, you will get the density. But you have information about quantum fluctuations in the shot-to-shot fluctuations. And you can use it for, getting more information about your system. We used it to train a machine learning model, for instance, to regress observables. Then you can get also entropy measures from the coefficients, but also from the natural occupations. The coefficients are basis dependent, so it might be slightly less useful in a sense, but the natural orbitals, those are invariants. So they're the same no matter the representation of your state. So that really gives you the entropy that you're looking for. And then since we also have implementations with cavities, you can add information about cavity order parameters. My computer will sleep soon unless plugged into a power outlet. So I need to go and get some power. Sorry about that. Be right back. Unless, can I use this maybe? Yeah. Thanks.
What are the things you cannot calculate?
Well, there are many things that are not implemented yet, like entanglement entropies, but you can, in principle, calculate them if you know how to get them from the many-body state.
Mm-hmm.
So anything that you can get from the many-body state, you can calculate because we have the full many-body state. And that in principle gives you the entire description of the system. So I guess you can probably calculate any quantity you want.
But I mean, this is just kind of sugar on top, right? Because your next is the simulation that gives you the state.
Mm-hmm.
And all these calculations you do with the state
are relatively trivial in the sense that, yeah, you just need to a way to extract information from the state.
Right.
But once you have the state, you have everything, right?
Right.
But it's more a matter of what is already implemented in the software and what is not, I guess.
User convenience.
Yeah. But already, all the things that I mentioned are already there. So you don't have to just do anything else. You can just calculate them and that's it. Okay, let's come to the software structure itself. So the software works with an input file and by running executables. So you first modify your input file. You decide how many particles you want to simulate, the number of orbitals, the various parts of the Hamiltonians, and so on. And then you run the executable. MCTDH-X is a collection of Fortran modules. So it's written in Fortran, in case you didn't notice when during the installation. So it comes pre-compiled. So when you install it, the program compiles your executables, and then you can just run the executables. You don't have to reinstall anything else. You only need to reinstall things if you modify the code to include, more features or something else. But you can just run the executable, ad nauseum. And the only thing that you need to change is the input file. So it's the only thing that you will change today, at least in the tutorial. The installed software comes with the predefined analysis. I don't know if you noticed when you installed, it created some comments in your bash RC or bash profile. I think it was bash RC file. Basically, if you type bincp or mcp, it will automatically copy files in your folders, so you don't have to do it manually. You can just use these comments. bincp will copy the binary files, so the executables, to the current directory. And mcp will copy the input file that you need to modify to define the simulation. And this is an example. So I type here bincp, mcp, and then I show a list of things. And I have these two input files that are characterized by the .imp final part. And then those two are the executables. So one is the input file for relaxation and propagations. Analysis.imp is the input file for analysis, so to get the observables. And then the same is applies for MCTDH-X GCC. This is the executable for relaxations. And the analysis one is for the analysis, self-explanatory. So let's have a look at the input file. I will kind of exit presentation now and look at the input file. But since I have the other desktop on Zoom, I need to create a terminal. And bring it here. Okay, is it big enough? You can see. Let's go to the desktop. Should be a folder called test with this input files. So we can have a look at what they contain. So this is a very lengthy input file. You don't need to understand all the points. I mean, when you do the tutorial, you look at it again. So there is different parts. They're kind of specified directly in the input file. There is system definition. Then if you go down, you will see, actually I can scroll faster like this. You can see there is different sections for different types of simulations. There is a part for artificial gauge fields, multi-level treatment. This is for systems with internal degrees of freedom. This is BC cavity coupled treatment. So there is many parameters. You don't need to modify anything in that if you don't deal with those simulations. There is other things like optimal control theory and so on. The things that are interesting for you are the part that starts with DVR that tells you the discretization of the system, the integration variables, so how to control the integrators for the orbital and coefficient equations of motion. And then there is the definition of the potential, and then the definition of the interaction. And then at the very beginning, there is some kind of overall system definition quantities. So this job type tells you what type of particles you're simulating, whether it's boson or fermions. FCI is full configuration interaction is deprecated, so you don't need to worry about it. Then you have M-orb is the number of orbitals that you want for your simulation. N-par is the number of particles. X lambda 0 is the strength of the interparticle interaction. Mass is just the mass of the particles, which is kind of like always renormalized in the units of the program. So it's always 1. You don't need to modify that. Job prefactor is important because it tells you whether you're doing a relaxation. So if you're doing imaginary time evolution or real-time evolution. It's defined as literally like a complex number, but in like a ordered pair structure. If it's -1, 0, then you're doing relaxation. So you're going to the ground state. And if it's 0, -1, you're doing propagation forward in time. You can also do it backward in time if you want. But I mean, I never do it, but it might be useful in principle. Then guess is another important thing. Guess tells you the initial state, how you start the computation. If it's hand, it's given by basically by hand. So the program chooses it by hand. Now maybe it's too big. I need to resize the window. There's parts to go. Yeah, so you see here, you can start from the initial state specified in get initial orbitals and get initial coefficients, which are routines that are contained in a certain module that you can modify yourself if you want, like Lucas was asking. But otherwise, if you want to start from a previously obtained computation, you use this guess equal bin. That stands for binary. So you restart from the binary files. You can also restart from some ASCII data that the program computes, and that's guess data. So this is the kind of like the main part that you need to understand to start up your computation. And then the other part that is important for you today will be to define the spatial coordinates of your system. So this tells you the dimensionality of the problem and how many points you choose in the discretization of space in each direction. In this case, I always recommend to give multiples of 2, powers of 2, because of some discretization errors that come into play when you go from like a base 10 to a base 2 in the computer. And then this tells you, this DVR-X, you don't have to really think about it. It's how the program collocates the discretization. We always usually we use number 4 because it's kind of like the most consistent. There's other ways. There is a harmonic oscillator DVR, sine DVR, but it's not really that important. And then you also need to specify from where to where your simulation will take place in actual space. So if you want to simulate from -8 to 8 or from -16 to +16 or something like that. Then there is a part about the integration. So that tells you how long the simulation will take place. So the starting time, the final time, and how big the integration step size are. So this is like line 150 here. So typically for very refined calculations with strong interactions and so on, you want a slightly smaller step so that you can kind of capture changes. But then, yeah, all these other quantities, you don't really need to think about it too hard today. Those are ways of kind of tuning the integrator, defining how big the integration space is and so on. The other thing that you need to know is how to define the potential. There is around 50 preset potentials, one-body potentials that are already coded in the program. They have all the specific acronyms that are contained in the manual. So HO1D stands for harmonic oscillator 1D. So that describes just like a simple parabola. And then it only has one parameter, which is parameter 1, that describes the width of the potential. It's basically the omega in your harmonic oscillator. And you can also have this in 2D, in 3D. You can have many more complicated potentials, sinusoidal with barriers, all the works. There's like a lot of them. And then
How do you code your own potential?
we'll count that in a second. And then there is the interaction type. That is the interaction part. If you're doing calculations with contact interactions, you're supposed to be using interaction type 0. All the other types are listed here. It just tells you how the integrator or how the program handles the interactions. Because, so if you have only contact interactions when you do in the actual integration of the interaction overlap, one integral drops out because you have a delta function. So then the program does not do the integral explicitly, but does something a bit, quicker.
But if I would take a periodic potential
Mhm.
and I fix maybe if I want to get the orbitals like linear functions or something, then I should use periodic boundary conditions.
So this is actually a very good point. The program is always using periodic boundary conditions. So that's like a standard default. If you want to look at open boundary conditions like a finite system, what you need to do is typically to add like very high barriers on the left and on the right, and then leave enough space from the barrier to the end of the simulation grid, such that there is not a lot of self-interference around the periodic boundary conditions. But the periodic boundary conditions are there to start with. They're always there.
And if I take the periodic 1D problem and I want to find the linear functions, I can get that from this code in principle.
In principle, yes, but it's not guaranteed that you will find them because you have this like time-dependent optimization.
Yeah.
So you might not necessarily get to the linear functions. You might get to something that is slightly different, and it might also be delocalized.
Yeah, so that's what I think, because do you get to what kind of orbitals we get? Will we get block waves or linear functions?
It's really kind of impossible to predict because it depends on the simulation optimization procedure. So yeah, I mean, I know that the method struggles if you don't have interactions, because you're using interactions in your equations of motion. You have this I don't know if you remember, there is this rho -1, there is an inverse that you have to calculate, and that sometimes can lead to zeros, and then it doesn't converge very well. So it's typically best to have at least some tiny interaction to make the convergence, the integrator work best and faster.
What is that forbidden interaction type 9?
It simply doesn't exist yet.
Why did you do interactions like 10?
I don't remember. I think because somebody said to me that 9 was already occupied. So I did 10, and it actually turned out that there was no interaction 9. So now there is an empty spot. If you have some like great idea, we can fill it. Yeah.
Where do you define your basis set?
The basis set is defined self-consistently in the optimization procedure. Oh, what do you mean? The orbitals. No, they are defined, they're optimized. You can start with the guess if you want initially. I think the initial guess is to populate some of the orbitals kind of randomly. But then they're optimized self-consistently from the equations of motion. Yeah.
From your history intro, this was originally software for molecular vibration.
Yes.
But from what I see now, that's no longer part of the scope, right?
No.
It's very positional, right?
Yeah.
Good.
No, this is really just, that's what Axel kind of constructed in the 2014 and so on, based on the MCTDH-B protocode that was done by Alexei. So this was really from the get-go, it was a code for quantum particles, so bosons, and then the fermions were added later.
And do you have Coulomb interactions?
Yes. So let me come to this interaction description. So here it is, the interaction type is how you handle the interaction in the integrator. So if you have, like I said, contact interactions, then one integral drops out, so you do computations a bit differently. So you use interaction type 0. Otherwise, if you have a product of interactions in different dimensionalities, you can use interaction type 1. Typically, what we use is 4 and 7. Those are to handle long-range interaction, and then the interaction matrix elements are computed with the fast Fourier transform procedure, which is kind of like highly optimized. And then, yeah, there are different kinds of types for different purposes. So if you know exactly what you want to look at, there is a specific method that is optimized for that. And then in which interaction you determine the actual functional dependence of your interaction. So if here, for instance, it's Gauss, this is kind of overwritten by the fact that you have zero, because zero always implies delta. But in this case, Gauss would mean like a Gaussian interaction, so like a kind of extended delta. You could have Coulomb, like Jonas was asking. You could have dipolar interactions. You can have anything you want, and you can also code your own type of interaction.
You can combine, like in, well, that you can have the point interaction and dipole.
Yes, you can have both. This is interaction type 7, where you see that you have a contact interaction, so delta, plus this FFT of the long range part. So you can combine both. Yeah.
So I'm coming from a very different perspective, since I'm doing molecular dynamics. So this potential, is that the potential that kind of all particles move in? Or, so you assume that all particles are moving in some external potential?
Yeah, this is the one body potential. This is this one. Yeah.
Okay.
They can also be time dependent.
And they can be different for different particles or in your system? Or?
I mean, in principle, yes. If you have, so we have this multi-species part of the code. So where you have like spinor condensates, for instance, so bosons with internal degrees of freedom, then you can say that the spin up component feels a certain potential and then spin down feels a different kind of potential. So that you can do. We're now working on the same for fermions. In principle, there was also Axel started working on something called the multi-species, where you have really just different particles altogether. It's not different components of the same particle, it's different particles that could also feel different interactions and different potentials. But that part of the code is not complete yet.
And can you combine the bosons and fermions then?
I guess so, yeah, in principle.
And interactions is how the particles interact.
Yeah, interact with one another, the same class of particles, if you want.
How do you specify kind of the kinetic energy operators of your particles?
So that is already specified. You do not modify it unless you want to add gauge fields. So if you want to add like magnetic fields or something that modify it, you know, with Paolo's substitution, and that is done in here in this artificial gauge field. So that if this is true, you can set an additional component minus omega I, where I is your gauge field, to the gradient part of the kinetic energy. So this is done at this level. And you can also use it to induce rotations, for instance. So if you want to look at rotating systems, then you have this additional centrifugal force term, but then it's added in the kinetic part from this artificial gauge field part. So it is there, but it's kind of like a bit hidden, yeah, because it was not really mainstream in the usage. And yeah, I think we're basically done. I just wanted to give you an overview of the input file. I think I mentioned mostly everything. Yeah, so interaction parameters here are just a collection of up to 10 parameters that you can use to specify your interaction. So then you can change them dynamically or change them you know, across different runs. That could be the strength of the interaction, but it can also be the power of the interaction. So if you have something like something that goes as, you know, 1 over x minus x prime, this is like the position to the power p, you can also specify p, and you can then probe different type of powers. So you can really just choose any parameterization of your interaction and just add it. Okay, so I think we can close this and go back to the presentation. Never see the cursor out here. Okay, we discussed this. Now let's talk about the source. This is a bit more advanced if you want to, add things yourself. There is another alias, CDMX. If you just type CDMX, that will bring you directly to the source folder, or actually to the main MCTDH folder, which contains a source folder marked here. If you're a beginner, you don't really need to worry about the source, because you can just do a lot of modifications, from changing the potentials, choosing one of the preset potential, and changing the interaction and so on. So there is a lot that you can already do like that. But sometimes you want to modify or add your own one-body potential or interaction, like Lucas was saying. And to do that, you need to locate this in the source, this ini-guest-pot folder. And in this ini-guest-pot folder, there is two Fortran modules, one called get_one-body potential, and another called get_interparticle_potential. So the first one contains all the potentials that you can define. So you can add one of your own if you want. And then get_interparticle potential contains the interactions, and you can also add one of them there. And we can maybe take a quick look at that. So I type CDMX. I am now in the main MCTDH-X folder, and then I can go to source. And you can see here there is many folders containing different things. The ini-guest-pot is the folder that contains all the modules that kind of construct your initial guess and initial potentials. And if I want to modify one-body potentials, I go to this get one-body potential. Then I can show you a couple of things. So there is a bunch of definitions at the beginning. And then it's divided in 1D, 2D, and 3D potentials. I don't know, let's look for something rather easy. So this is the part that starts with defining all the potentials. So which pot, if you remember, this is the variable that describes, the name of the potential you want to modify. So this is something that I added some time ago. For instance, this is an optical lattice with hard walls in 1D. So you have basically just like a sine squared term with the parameter 1, parameter 2. So the parameter 1 is the amplitude, the 2 is the period of the sinusoidal change. And then it's only defined within two walls. So if parameter 4 and parameter 3 then describe where the walls are placed. And then if it's outside of these walls, the trap is just very large. So basically it just describes something of this kind, right? So just a very high wall, then some sinusoidal potential, and then another very high wall. This is one example of a potential that you can describe and you can code.
Depending on where is put the walls, if the distance between if you don't have a periodic potential there, then you have a wavelength, what you can fit in. And if that is not rational with the period of the optical lattice, I guess it will fit the results. So I could imagine that it's important where you put the walls.
No, not necessarily, in the sense that if you use a fine enough resolution of your space, it should be okay. Because you have to imagine that this potential, what I drew is actually everything is discretized. So it's like, it's actually a set of points. So if you have a tiny enough resolution, there will not be too many incommensurate issues.
If you are not feeling the walls anyway, then it shouldn't matter. But if you really if you get the characteristic length scale from the walls, and if that's not commensurate with the length scale of the lattice, I could imagine that it could.
Well, okay, no, and I understand what you mean. I usually just put the walls, yes.
Yes, you make them.
I make them exactly at the top of one of those, right?
Yes,
so I actually make them here, yeah. Yeah, no, now I understand what you mean. Now, if you just shift them somewhere, then it can be a bit messy.
Yeah.
But that's something that you can control by defining these parameters 3 and 5.
If you have enough periods, does it matter where the wall is?
I guess it depends on how detailed you want to be in what you're looking for. We have had things where when you have two competing scales.
Yeah. And then the thing that I said before, it's important also that you consider that this is your potential, but then there is something behind it that is actually the simulation grid, and you have to leave enough distance between the wall and the simulation grid to avoid kind of like this particle feeling itself across the periodic boundary conditions. This is very important if you're dealing with like long-range interacting systems like dipolar interactions and so on, because then the distances become really important.
Yeah.
Or even Coulomb, that is
That's
even more
actually a
long
fun
range.
problem if you have dipole particles on a ring.
Yeah,
They can interact over the ring.
exactly. Yeah. So we had a look at the potential. I can also show you the interaction. Let's see, look for reg C. This is regularized Coulomb. So here you also have, some definitions at the beginning, some, variable definition in portrait and so on. And then you come to a bunch of different interactions that you can define with given names. For instance, here I show you the regularized Coulomb, where it's supposed to be a regularized Coulomb. This is it's some square root 1 over square root plus some other parameter which has an exponential. Okay, it's something a bit different, but yeah, let's take this one, which is the one that I use for dipolar simulations. Here you have this type of form that I kind of drew here with an additional parameter here. This is like thing parameter. So it's 1 over parameter 1, parameter 3, parameter 2. Okay. So this is parameter 1, parameter 3. It doesn't really matter anymore. Parameter 1, parameter 3, plus parameter 2. So this is the type of interaction that you can code. And then the strength is given typically by lambda 0, which is something that you define at the very beginning of the file. So you can have this type of interaction and modify any of those parameters. You can go from Coulomb to dipolar to something quartic, whatever, and you can also add regularization factors to avoid, divergences when x equals x prime. So this is, you can do anything that you like. You just need to add your own name for the potential and, code it in this way, and then it's done. Then you have to recompile the program, and then it should work.
What is this ions?
Yeah, there was also, I don't know if it was Axel who coded it, but somebody coded something for anionic statistics, but I never used it, so I don't know. But yeah, there is something there. So if you're interested, maybe you should look it up. Okay, so we talked about the interactions and so on. Less often, you also might want to define your own custom state. The default is random, like I said. This is less relevant if you're doing dynamics because it's optimally, so you start from a state and then you just time evolve with something. So you always need to provide an initial state that you usually get from the relaxation. But for relaxations, you might want to start from a state with certain symmetries, like we discussed, or something that will converge faster or easier to your ground state. And then you can do it, yes?
I haven't seen any time dependence in the Hamiltonian where the interactions yet.
No, but you can put it, it's there. I mean, you can.
So that's how you would then code a relaxation.
And what do you mean, code to
You
relaxation?
said generally you start from a random state.
Yeah.
Then for these kinds of propagations, you would first do a relaxation and then repropagation.
Mhm.
So then you would have to have some time dependence, right? First the relaxation.
Well, you first do the relaxation to obtain your initial state, and then you propagate it, and then you do have the time dependence. You can have a time-dependent Hamiltonian, and just the initial state, you choose a state that you relax from a different simulation. That's what I mean. Yeah. But actually, in the tutorial, you will use you do a quench, so you will use a time-dependent potential where there is a barrier that is raised in time. So you will actually use a time-dependent quantity. So if you want to modify the initial conditions, you need to modify these two files, get initial orbitals.f or get initial coefficients.f, and those also contain an INIGES spot, the same folder that we saw before. Finally, if you're very advanced, you might want to add your own observables. So we discussed that there's many already, but maybe you want to add something, like we said about out of time correlations and so on. So you need to look into the folder analysis, and then there is some modules that contain the one body, two body, or many body observables that you can simulate. Then you can add your own. They are based on, a combination of the coefficients and the orbitals, if you know how to get it from there. It's important that whenever you do changes, to remember that whenever you do changes to the source, so you modify, create new potentials and new interactions or new observables and so on, you always need to recompile, so to reinstall the program, because it comes with the pre-installed executable, so you need to reinstall, rerun, and recreate the executable. And the integrator we discussed before, so we don't really need to go through it. Now, just a couple of words about the workflow, how you usually do simulations, or you will do it this afternoon. This is kind of like a nice summary of the workflow. We discussed the source files already, so there are different files you can modify. This is like for advanced users. Then the first part is always to define the inputs. So modify the inputs to describe the problem that you want to describe. Once those are modified, you run the executables, either MCTDH-X or MCTDH-X analysis if you want to get observables. And typically the task is to first compute an initial state. That could be, let's say if you want to do dynamics, right? Like we said, you first compute an initial state within a relaxation or with, the custom initial states, which is here, initial conditions. Then you can optionally analyze the initial state already to see whether it's correlated like I wanted to, or if it's localized in the wells like I wanted to or something. Then you use that to do the time evolution. So you rerun the executable with the new state. It's important to remember to modify certain variables in the input file that I'll show in a moment. Then you run this time evolution, it's run, and then after that you can analyze it and extract observables from the many-body state. So for the relaxation, it's important to remember that you need to change this job prefactor to be -1,0. This is the improved relaxation. For propagation, so time evolutions, dynamics, there is 3 things that you need to take into account for the initial part of the code. You need to change the job prefactor to forward propagation. You need to change the guess from hand to binary or to data, so to use the state that you have relaxed to. If you use hand, it would just start from a random initialist, from that random noise. So it would just propagate noise. It's something that always happens, and it still happens to me sometimes. So you really have to remember to always change this guess. And then you also have to give a binary start time. This should correspond to the last time in the previous relaxation that you've done. So if you've relaxed from 0 to 50, then you should give time 50 as initial state for the new relaxation, because this will be contained in the binary information that you provide. So this is very important to remember. And then There is a couple of other things to remember. This is more like to improve convergence in the integrator. You have to change the integration step size. So for propagation, like I said, you preferentially want smaller time steps to avoid accumulation of propagation errors. And then you need to change the coefficient integrator from the Davidson, which is the stav string, to MCS, which is this other optimized integrator that deals with sparse matrices. And finally, for the analysis, we said that this is done separately. So you first do relaxation, then you do propagation, and then you can run the analysis separately. This has also a separate executable, like we said, MCTDH-X analysis _ GCC. And observables are calculated every time that you provide in the relaxation or propagation. So you cannot calculate, let's say you have relaxation or propagation that has time step 0.1. You cannot calculate observables that are smaller than that. So you cannot calculate at 0.01 because there is no information about that. The observables that you can calculate are divided into zero body. This is energies, where you can re-output the orbitals and coefficients. The one body is our density in real momentum space. Two body or correlation, structure factor, and so on. And then many bodies, anything that involves the entire set of states, like fidelities, single shots, entropies, and so on.
And you can compute this, and like you said, you can compute this at time steps that are larger, because...
Yes, that you can do, yes. So actually, I can show you the input file now about the analysis. So I go back to the desktop. So the input file is this analysis.imp. So you see that here there is this time from, time to, and time points that tells you at which time step you calculate the observables. So if you have in your calculation something that goes from 0 to 10 in steps of 0.1, then you will have 100 points. But you can also just calculate observables from 0 to 10 in steps of 1. So you just do 0, 1, 2, 3, and so on. And then in this case, you would say from time 0 to time 10 in steps of 11. And number of points, it's always this. So the time to minus time from divided by time points. So if you have containing both the initial and the final time. So you always have to add 1 plus 1.
Just to be sure I understand this. There's now two different kinds of time steps. These time steps, which is how often do I save the state while simulating, and the simulation step that is usually much smaller.
Yes.
Okay.
Yes, that's correct.
You mean t points minus 1, or t2 minus t from divided by t points minus 1?
Yeah, there is a -1 missing, or I think it's, yeah. So these are always included, 0 and 10, so the initial and the final. So you always have to add +1. Yeah, and so here you have, like I said, the one body, two body, and many body variables you can decide on to calculate the density in K in X space. So T is always true, it means like you calculate it, it's active. F means false, so you don't calculate it. So you have to kind of toggle on and off all these different observables. Correlations is self-explanatory. And then you have the many body, you have this entropies, single shots, fidelity, and so on.
So are these things you calculate at every step while doing the simulation?
No, you do it after. So you first do the relaxation and propagation. Then when it's done, you do the analysis, which is just getting the information about the observables with the many body function, many body weight function that you have at all these different time steps.
But isn't that lots of data, or you need to save lots of data?
It can create lots of data. It depends, specifically the correlations in higher dimensions. It can be gigabytes of data that are generated. So you have to always think carefully of if you really want things or not. That's why it's not generated automatically during the propagation, because in principle you could do it, but it can easily, you know, then creates huge numbers of very heavy files, and then you load your memory very fast. And so it was structured like this from the beginning to allow like a separation of tasks. So you first get the many-body wave function, and then it's typically not too heavy. But then if you want to get information about the observables and so on, that could be very heavy. For the correlations in 2D, you have to imagine you have, let's say you have 128 grid points by 128, and you want to calculate the correlation with everything, then it becomes quite heavy already, right? So then typically what you do, you define cuts. So you define, okay, a cut at this point, and a cut at that point, and then I only calculate that correlation. Then it's a bit less data. And yeah, I think, oh, I modified something. I think that was it. So we can maybe take, I'll take another small break, 5 minutes before continuing. Yeah.